Hi, my name is Albert Dunford, and in this tutorial video we are going to implement this single-phase inverter, and we are going to close the control loop. So we're going to implement an average current mode controller on the current flowing through the inductor right here, and we will also then close a voltage loop, an outer voltage loop. So two-loop controller, and we'll try and do this as quick as we can. So first things first is I've left the default values here for the inductor, capacitor, and resistor, and so let's size these components properly. So we'll pull up the current scope for the inductor, and we'll pull up an oscilloscope here for the output voltage, so the voltage across the capacitor or the load, and let's also set up our load properly. So what should the load be? Let's quickly pull up the calculator and figure it out. So if we're going to do 120 volts RMS, and we want to do 3 kilowatts, then we need a 4.8 ohm load. So let's put that in there, 4.8. And 120 volts RMS, let's quickly check what's going to happen there. So our, let's also put up another probe here for the carrier waveform, V car, and then this one is VMA, and we'll put your display. Okay, so what we're going to do first, though, is before we look at all those values, is we're going to run this and look at the values on the oscilloscope here and on the on the voltage scope that we have got on free run mode. So what free run mode does is it prevents an end of the simulation, so it's just going to run in perpetuity, and we'll be able to watch these signals in real time. So off we go, and we've got it set to Autoscale right now, and things will settle out. So first things first, let's see if we've got 120 volts on the red line here, and we don't, so let's just adjust that on the fly with a runtime variable. So okay, 0.6 looks pretty good, and over here we've got 25 amps, it looks like. So let's put that to 0 and swap to AC coupling, and we'll also swap the inductor to AC coupling as well, and turn on Autoscale again, and we should be able to zoom in a little bit here and see what's happening. Okay, maybe a little bit lower. So we have 25 amps, and so right now the current ripple is 200 milliamps on 25 amps, and our voltage ripple is just over 100 millivolts peak to peak. So let's play with the inductor a little bit first. So we don't need quite this level of ripple suppression, so let's go to maybe 500 microhenries, hit apply, and we see how things adjust automatically. So now we've got 400 milliamps peak to peak, so about half an amp of ripple on the inductor. That should be okay. And over here we're looking at the voltage ripple, and it is on 120 volts. We're looking at 200 millivolts, so maybe we need a little bit more capacitance. So what's that now? 20 millivolts, maybe a little bit more. So that is 40 millivolts peak to peak on 120 volts, which I think should be okay. Let's go with that. So 500 micro and 7 microfarads. I don't really have any particular I don't really care too much about what these values are. They just have to be something. So we'll stop that simulation and we'll go and we'll put this back to free run. And we're looking at a 1.1 microsecond time step, and we'll go for 10 milliseconds, and we'll see what happens here. So VMA looks good. Obviously it's flat. Let's pick up the carrier waveform so you can see what that looks like. We'll actually plot it onto this one, the carrier, and we can zoom in here and see. So our carrier waveform, 100 kilohertz, 50% duty cycle, 1 to -1. And we can see 25 amps up there and 120-ish volts there. And that looks really good. Let's redraw it back out, and what we're looking at over here is where we hit steady state. So we're at steady state within 500 microseconds, but we should be looking at our maybe a load point in the middle here. So if we look at 48 ohms load, so 300 watts, we should see a different interaction, and we do see that. So let's just delete this screen down here. Screen, delete screen. So we can see a little bit of ripple before we hit steady state, and steady state occurs around 4, we'll call it 5 milliseconds. So what I'm going to do is I'm going to set up an AC sweep, and we'll look at doing a sweep with the 48 ohm load to pick up the open loop plant response. So to do that, we'll slide this out. We'll grab an addition symbol. We'll grab a source, a sine source here. We'll go over to other. We'll grab an AC sweep multi-sign block, and we'll grab a probe for the inductor current. Okay, great. Inductor, and then down here, vSign 1, we'll copy and paste that name over to vSign 1. We'll go into here, 100 to 10K. Let's go up to 50K to start with. We don't need quite that many data points to start. 5 milliseconds is where we hit steady state. And our amplitude will go start at 10% of the perturbation. So that should be good to start with. 100 to 50, 20 points. Okay, that looks good. Let's run this and see what we get here. Okay, this is a great starting point. I can see there's a lot of resonance here, so maybe we want to reduce the size of our perturbation. We don't seem to have an issue with attenuation at higher frequencies. So let's drop this down a little bit, the perturbation, to 5%. Let's add in a bunch more points, and let's go a little bit higher and see what we have now. And this looks pretty good still. Yeah, we're stabilized in the phase. Our amplitude is going down still, and what I'll do now is, because we need some lower frequency points, I'm going to drop this number down now to a lower frequency number, and we'll bump up the points again to make sure we get that nice resolution on the resonance peak, and we'll run it, and this will take maybe 20 seconds to run. So we'll pause the video right now, and we'll come back when the simulation's done. Okay, so here's the sim result. As we noticed down here, it took about 18 seconds to run. We've gone from 10K up to 70K. We've got a nice resolution of the phase transition, and what we're going to do, so this is the single phase inverter.fra file, is we're going to load this into SmartCtrl. SmartCtrl being a handy tool for control design, and we'll pull that up here. So here is SmartCtrl. I'm going to load a new document. This window will pop up. I'm going to grab this frequency response. We're doing current mode control. Grab topology, the sweep file. So we were originally doing 25 amps, but then we did that sweep at a tenth of the load, so that's 2.5 amps now. 100 kHz, hit OK. And sensor, we are a current sensor. We'll eventually get up to the full load, which is going to be 25 amps, so we'll go 1/25 to start with there. Compensator, PI, where our waveform, remember, is 1 to -1 at a 50% duty cycle, which is what those are for. So positive max, minimum, the minimum, and then the duty cycle, or the rise time, and then we hit set, and then we get to choose an operating point in here. Okay, okay. And so this is what we see here. So let's pull up. The brown line is giving us our closed loop response. Pink is control to output. Green is the open loop. Our polar plot here, and our step response here. So there's an error in the DC value here because our frequency sweep didn't go down to 0.1 or 1 hertz. That would have taken a long time to run and really doesn't provide too much extra information. So we can get a good idea of what's happening here just by playing around with this number in here. So I think something in here, so that's a cross frequency of about 20K, phase margin of 52, so this is giving us our stable operating zone. So I'm looking at the brown line. It looks nice and flat. The phase response is nice and flat over the frequency range that we care about, so 60 hertz. Our step response here looks pretty good as well, and we've got lots of DC gain, and maybe a little bit slower. Yeah, something in there. And we've got good attenuation of the switching speed as well. So we'll use these values and see what things look like. So how are we going to use these values? Great question. So let's just move this out of the way and make a little bit of room over here. Slide that over, and we will grab a multiplexer. What the multiplexer allows me to do is essentially switch between open loop and closed loop simulation so that we can check things and iterate the design easily. So I'm just going to put this in, and we'll slide that over here. Well, actually, what I'm going to put in to begin with is a limiter. So in the end, all we care about is -1 to 1, but maybe we'll reduce the maximum and minimum duty cycles to 98%. And let's put this now a PI block, and we'll move this again sort of out of the way a little bit more. Give me lots of room to work. We'll grab a DC source here. So this is going to select between open or closed loop. We'll wire this in, and then we need an error amplifier or an error signal, and we'll grab this guy over here, and we need to set up a label. So let's go I sense. I'll plug it in, grab it, and bring it over here. And then also we need to remember that we gave ourselves a gain of 1/25 on the current feedback. So we'll put in a gain block here and multiply this by 1/25. And that should be essentially everything for setup. So we want to grab the these values here, KP and KI. Oops. So 18.487, and the TI or the time constant was 11.1396 microseconds. 11.396, 18.4847. Okay, well, the sig fig doesn't matter too much there, and we'll disable this sweep block, and now we need to worry about what reference we want. So we want 2.5 amps, but our gain is 25, is 1/25. So 2.5 divided by 25 is going to be 0.1. So we'll go here, and this should be 0.1. Okay, so one last thing before we run this is we'll just put up a probe onto one of the gating signals, and we'll call this QA, and we'll now run this simulation. And so let's look at the output voltage. That looks pretty good. Let's grab the current. We'll grab carrier and modulation, and we'll also grab QA. So let's zoom in on what's happening here. So this looks okay. It looks, we could do with maybe a little less ripple on the modulation waveform, but we'll survive. It looks like we've got 100K still okay on the switching, on the gating, which looks good. We've got our, let's do a waveform here. So we've got 200K hertz of ripple on the current and the voltage, which is about what we're expecting. And what else can we mention here? Yeah, this looks like it'll be okay. Yeah, if we wanted to do a little bit better, we could try to get VMA to be a little bit more stable, but this will be good enough. And to get that more stable, we would reduce the speed of our controller a little bit. So what we're going to do now is play with, and let's also just check to make sure that our full load value is good. So we'll rerun here, and then this we will have to adjust up to 1, and we can run this one now, and we can see that things are still looking relatively okay. 120 volts, I sense 25, and things are still looking reasonable down here as well. So that looks okay. And then the final check for this would be obviously to convert the source to a sinusoidal source to see how that works. And so that would be 0. And then this would be 1. And let's run this now. Oh, we need to run it for a little bit longer. Let's go for 03. We'll pull up a runtime graph window and see what that looks like. And that looks really good. So there we go. That looks acceptable. And what else can we look at? Maybe if we look at the lower value as well. So that would be 4.8, and then this would be 0.1, and we'll run again. So this should look pretty good as well. Okay, so that is essentially what's happening with the control so far. So the next thing is to set this thing up for the next sweep, which is the sweep of the open loop. So our reference here will be 0.1 again. I'll just quickly delete these guys. Actually, I could have used those. So we need a new sweep block, vSign2, we'll call this one this time. This name needs to match again. So it'll be 0.1. So we'll take a quick look through at some sweeps first. This can be 0. We'll just do an informational sweep to start with, 100 to 50K with 20 points. And we also need to check where steady state is on this DC value here. So looks like we should hit DC pretty quickly by 5 milliseconds. So we'll put in 5 milli here. And what else can we do? Oh, we need to set up this AC probe over here on the output voltage. V out. And we will disable this one. Okay, so that is everything except this. Let's go down to 10% again. And we'll run the sweep, and we'll see what the results look like. So that looks pretty good. Lots of gain, lots and lots of gain. So we should reduce this down a little bit, 0.1, and go from a lower frequency and maybe add in a few more points. Okay, so I ran a couple sweeps there, and I ended up with these parameters. Essentially, I was trying to get the higher frequencies to smooth out a little bit while not putting too much amplitude in because of the amount of gain we have in the system, so 60 dB of gain. And we will open this up into SmartCtrl with a new import frequency response. It'll be voltage mode controlled, okay. And we'll grab single phase inverter, hit open. Output voltage is 120 volts. Our switching speed is 100K. We'll hit OK on there, and we'll load a sensor, an isolated voltage sensor. So 120 divided by 1 whoops, 8.33 milli. Hit OK. We'll go for PI here. And now this is the fun bit. Well, we'll get to the fun bit in a second, but we're going to go from 1 to 0 here. So a peak of 0 to 1 and a duty cycle of 98%. So essentially a full ramp waveform. And the reason why we want to do this is we need to scale the output properly. So we want the output of the PI controller to essentially be scaled in such a way that if the outer loop was the only loop that was working, it would ask for 60% duty cycle. So if we go back to here, the open loop set point is 0.6. So we want this controller to think that it wants to give 0.6. So yeah, so 1 to 0. So this will, if we were to set this up on DC, it would be giving us 60%. It would be the final point. So we'll hit OK here, and then we'll grab something in here. Hit OK, OK, and just grab the other monitor over here. Set this up. OK. We are going to move this point around. Grab something in here. I think something like, so that's like 40, 60 degrees of phase margin, something like that should be pretty, good, I think. And this looks pretty good as well. So these values we'll go with. If we need to redesign, we'll come back to it. Okay, we'll move that out of the way. And so here's our parameters we want. So we'll come down here and we're going to add in a new reference. We want 2.57471 and 58.399 micro. And we'll grab this setup as well. And we want vsense. And I've already set our gain up with 1/120. And we'll grab a DC source for now. We'll set this as 1. We'll disable this block. And I'll disable this. I mean, I could have set up another mux, but we'll just leave it at this for right now. And here's the trick. So we're all set to run the simulation. So let's run this now. And we'll pull up a runtime graph window. And we should see, yes, it doesn't work very well at all. And the reason for that, if we take a step back, is this controller thinks that the set point should be around 0.6, but it's actually around 0.1. So we need to put in a gain block here and go 1.1 divided by 0.6 and rerun, and now we should get a nice and stable solution, and we do. So that looks pretty good. And next up, we should always zoom in and make sure that our controller is stable and the duty cycle is stable, and it is. Rescale, so everything looks pretty good here. And let's now swap this out for a sinusoidal source and put this in here. So we'll go 1 to 60, and we'll so we should see now, and we'll grab this as well, runtime graph. So there's the current, there's the voltage. Those look nice. Let's rerun at 4.8, so our original maximum load. We can see that this looks pretty stable as well. And then also let's go down to a lower load and see how that looks. And this looks pretty good as well. So this looks to me job well done, although we do need to scale this voltage a little bit more. So let's change this actually and put in the square root of 2 here to get the RMS value. So 1.5 414 and rerun. Whoops, I missed a decimal point there. 1.414, rerun, and we can see, yes, that does look nice. And yeah, so the look for another video. I'll digitize these controllers, which would set this up nicely for some code generation. And if you're wondering if this works at 50 Hertz, well, let's run it at 50 Hertz as well, and just make sure that that looks okay there. So there's 50 Hertz. Looks good, and we'll bump up the load to 4.8 again, so the full load now, and that looks good. Okay, well, there we go. So there's our single-phase inverter, and with an inner current loop working with average current mode control, and then we close the outer voltage loop with another PI controller, so inner current loop at average, and an outer voltage loop as well. And yeah, that's it for this tutorial video. Look for an additional video where I digitize this controller. Okay, thank you so much. Bye now.